In the next section, we return to the depth-bounded exhaustive search technique that we've seen before for a few introductory examples. And I have a few more examples that take some more properties of the input into account to do something that's maybe not completely obvious at first that it's doable, but they fit in this schema of exhaustive search as well. That's what I just said. There were the previous examples were basically simple brute force algorithms. And we'll try to look a bit closer now. This one I've moved, so you can't recall this. We will see. We'll see that the problem of independent set in a graph. So remember what that is. You're given some graph, undirected graph, could have cycles and whatever, could look complicated, doesn't need to be connected in general. The task in the independent set problem is to find a largest set of vertices that are mutually unconnected, so no edges between any of them. So what's a maximal independent set here? I suppose I have to pick these. I'm guessing it's a good idea to pick these leaves, but it's really a hard problem, so I might not get the optimal solution this way. Probably these two, and that's all. Oops. So I guess that's a maximal independent set in this case. Or maximum, I should say. That was the independent set problem. Now I haven't told you what W1 hard means. So just forget about it for the moment. We'll come to that probably tomorrow. We'll start with that part tomorrow. What this means intuitively is we shouldn't expect an FPT algorithm for this problem in general. Okay. As often in complexity theory, we can't really prove that. Same as for NP hard problems, we can't prove there's no polytime algorithm, but it's a bit unlikely. So what we'll look at here is a restriction of this problem where the graph that we're given is planar. And indeed, the example I've chosen is a planar graph, just because they're nicer to draw. So first of all, I'll define this a little bit because I don't know how much graph theory background people have. So it's the same problem, just that now the graph is planar. And the rest is the formalization of what I've shown on the example. We're given a parameter and we try to find k vertices that are mutually not connected. I've shown you the optimization version of the problem. Now, what's a planar graph? Maybe would be a useful question for Slido. Who knows what planar graphs are? Who doesn't know what planar graphs are? Have you heard the term before? So a planar graph is a graph that can be drawn in the plane like this without any edges crossing. So embedding is the formal term, but you can think of it as a placement of the vertices in just the Euclidean plane R2. And I'm just going to say a drawing of the edges. You can make this more formal, but maybe it's not needed here. No, stay. Now, if you come up with examples, maybe it seems like every graph should be possible to be drawn like this. A famous example that is not planar is the K33, the complete bipartite graph with 3 vertices on each side. So every vertex here connects to every vertex on the other end. But it's bipartite, which means all the edges go from one set of vertices to the other set of vertices. Here we have the lower and the upper vertices, and there's no edges that stay among the lower or among the upper vertices. And now the way I've drawn this graph clearly has edge crossings. Now the trick with planar graphs is all that counts is the graph with the set of vertices and edges. My drawing is just one drawing. Maybe there's a better drawing if I'm smarter with routing the edges. Maybe there is a way to not have them cross. But here the answer is no. There is no way, and provably so. And I guess we'll see in a second why. I mean, it's a classic and simple argument. Another example is K5, the complete graph of 5 vertices. A bit more messy to draw. Initially looks like a nice thing, but now, is that all? Yeah, it looks like everything has 4 edges. So that's the complete graph on 5 vertices. That's also not planar. And then there's a cool theorem that essentially these 2 graphs are the only obstacles. Whenever a graph is not planar, it contains a potentially concealed instance of one of these 2 graphs. That's a deep theorem in graph theory that we won't need for now. So you can forget about this. But that's a nice way to check if a graph is planar. So we're looking at this independent set problem, and maybe you can get an intuition that potentially this problem is easier on graphs that are not like this, right? These are forbidden now. Only graphs like this where I can draw them in the plane. Maybe you get a feeling that the problem might be easier on these graphs, just because things are separated out. If they're far away in the plane, then maybe there's also no edge between them, because it would probably cross a lot of things. But this is very vague. That's not the way to prove anything. What we'll show at the end of this part is that indeed you can do independent set on planar graphs with this running time, which is a fixed parameter tractable algorithm. And remember, for the general problem, this is unlikely to exist. So the restriction to planar graphs here really helps us. And whether 6 to the k is a good running time is a different question. I'll only show you a very simple algorithm, which indeed, this is the worst case. It's often much better. But how does this work? How can you exploit this property that the graph can somehow be drawn in the plane, which is not even clear how to construct this if you first see planar graphs. So how can we use this to do a faster search for independent sets? Okay. We'll use a bit of background knowledge on planar graphs, but it's all fairly fundamental. Now, I'm saying this from today's perspective. It all builds on famous results, including stuff from Leonhard Euler and so on, which at the time of their invention was, I guess, fairly non-obvious. But I can explain all the concepts on one slide or two. The famous result that Euler proved is summarized with this equation. Whenever you have a planar graph with the additional restriction that it's connected, again, algorithmically, that's not a problem. If I have an instance of my independent set problem with several disconnected parts of the graph, I'm just solving the problem independently on all the disconnected parts. And the independent set of the entire graph is the union of the independent sets of the parts. Right? That's what happened here as well. In my drawing here, the graph was disconnected. There was an isolated vertex, there was this tiny component, and there was this bigger component. And I could just independently solve the problem on each of them. So assume for this part that the graph is connected. Then it has n vertices, m edges, and f faces. That's not defined. There's the faces missing, which is in such a drawing is the regions of the plane that are cut off by edges. It's a very graphical kind of notion. Then you can relate these numbers, and in any connected planar graph, this equality holds exactly. It's a powerful tool. I'm not going to prove this, but I'm giving you some idea for the proof, because you can almost prove this inductively. So first of all, let's make clear that the terminology is clear. So I'm drawing a tiny planar graph. And there can be funny business like this as well. So let's quickly count the three quantities here. What's the number of vertices? Well, 1, 2, 3, 4, 5, 6, 7. Okay, you correct me if I'm doing stunt nonsense. 7. Then the number of edges, 1, 2, 3, 4, 5, 6, 7, 8. And the number of faces, now this is, maybe we can shade those a bit. There's one face. There's another face which goes around this vertex. This is still the same face, right? And then there's the outer face, which is everything outside of the graph. So we should have 3 faces. And now if we check the formula here, we have 7 minus 8 plus 3, which indeed is 2, right? 10 minus 8. So it works out in the example. That's good. That's not a proof, though. I'm not claiming a formal proof, but I want to give you an intuition because I think it's just so nice. And there's enough people that haven't seen, not to have seen it. So effectively, it's an induction on the number of faces. If you look at graphs with a single face, how can these possibly look? No graph can get rid of this outer face, the dark blue one. So the only option to not add another face is to avoid any cycles. As long as I'm never closing off a part, I keep one face, and whenever I close a cycle, I must enclose another face. So if I have a single face, then G is a tree. And then basically it looks something like this. It might branch off. It can have arbitrary degree, right? It can have long branches, or it can have high degree vertices. But it will always look something like this. And computer science basic knowledge. Question?
You said no graph can avoid getting the outer face. But
sure.
The one you draw, for example, has 0 faces.
Which one?
The one you draw.
This one?
Yeah.
It has one face, namely the outer face, right? But there's still one. So a face is a part of the Euclidean plane. And if it's enclosed by edges, then it's also a face. But also the thing that is on the outside of the graph is one face. An alternative equivalent way to view it is to see the graph embedded on a sphere. Then there's no outer and inner. There's just faces. It's very annoying to draw spheres and make it clear and visually, but if you have good 3D imagination, maybe you find it easier to imagine this wrapped on a sphere. And then this blue thing is just the thing that wraps around the back of the sphere. And it's not a special face in any sense. It's one of the faces that it has. And if you take a sphere and draw a tree on it, there's still the sphere. So, but it's a good point. I guess it's how to define faces properly is maybe tricky. So faces should be thought of as regions of the plane. Now, computer science basic knowledge is in a tree, there's one more vertices than edges. And the simple picture proof would be pick any vertex, say this one, and orient all the edges towards that guy. If they're far away, there's still a unique path because there can't be cycles. And once you've done that, every vertex has exactly out degree 1, apart from the poor guy we chose, which has no out degree, right? So here, always n is m plus 1. And if you plug that in, it satisfies the equation. Okay? So that was the induction basis of this induction. And then the inductive step is take any graph and a drawing and add another face. How can that happen? And it basically happens by closing another cycle. That's virtually the only way how you can add a new face. You have to somehow close a cycle. And that's the part where I'm just giving you some idea, and I'm not trying to do a rigorous proof. How could things look? So there could be many weird things how a face could be created. Maybe this is our graph that we start with. Currently has 3 faces, right? The outermost and these 2. Now, one way to create another face would be to close an edge here. That would add this face, and it would add 1 edge. Another option would be to draw an edge in here, which cuts one of those cycles in half, adds another face. Another option is to connect this one, but in each case, what I'm doing is add 1 edge and close off 1 cycle. So I'm getting a plus on the edges and a plus on the faces. That's the key operation. And if you look what happens here, the difference between faces and edges doesn't matter. I can add edges. If I also increase the faces by the same amount, I won't invalidate this equation. And you can think about what else can you do to a graph to grow it? Well, you can add vertices. If they're isolated or just connected somewhere, then they don't add a face. So if I'm adding a vertex here, something like this, I'm making n1 bigger, but also m1 bigger. And I don't get another face. Then again, the equation is satisfied. This kind of, I'll stop at this point. The idea is that this formula can be proven by going through all possible cases how you can modify a graph. And you can use induction on, say, the number of faces to see what happens in each case. Okay. So far, so good? I guess it's yeah, we normally don't allow loops where when I say graph, I think of a simple graph. Does it violate the formula though?
Like simple 2 vertices, 1 and self loop. Yeah. 1 edge and 1 self loop.
Like this?
Yeah.
So you have 2 faces, 2 edges, and 2 vertices. That seems fine, right?
Yes, right. Okay.
It seems right. So it has to be connected. That's definitely like the way to break it is to just say I have 2 vertices, or I have 4 vertices and they're not connected. Then things break. That's why the connected here is important. It's an interesting point what happens with self loops. For most of the algorithms, I think I'm implicitly assuming simple graphs, but I think this specific theorem would actually work fine. The same argument here seems to work. Right. Let me just do this in dotted. I'm also adding one edge and one face, so I don't think it breaks. Okay. What we use this equation for is the following simple observation, which again is something to keep in mind about planar graphs because it's useful in many places. And here we need simple. If I have a planar graph, a simple planar graph with no vertices and edges, I can bound the number of edges it can have simply by using that formula and the fact that faces can't be arbitrarily small. So what's the smallest face I can make? Well, I could try to do this, but that's not allowed in a simple graph. Then I would have a face that's delimited by just one edge. I could try to make a face that's delimited by 2 edges, but then actually these would have, again, they connect the same vertices. So this is also not a simple graph. So the smallest configuration I can make that closes off a face is a triangle. Okay? So in a simple graph means every face is delimited by at least three edges. And so whatever my graph looks like, I can just count how things go. So let me again do this mostly by example. Might actually be enough. So I have 3 faces, this one, and the outer face. I must have 3 edges, three edges for each of these, but I'm double counting each edge exactly twice. Right? Okay, I guess that's not true as I wrote it here. Summing over the edges that delimit a face would double count every edge twice. If I say I use the minimal number as it's at most. So I get a bound on the number of edges. But then I can also insert what I know about f. Let me move this a bit. So what do we get? 3 times, and then it's 2 minus n plus m. I'm just solving this for f, and hopefully don't goof by doing it. And so stay here. That's the overall thing. Now you can simplify this further. So it's 6 minus 3n plus 3m. So you now have the entire equation, and I'm subtracting 2m from this. So I take this equation, minus 2m, and bring this part to the other side. So also plus 3n minus 6. So I'm left with m on this side, and on the other side here I get less or equal 3n minus 6. Is that clear? I'm just taking this one equation, right? 3m greater equal 6 minus 3n plus 3m. And moving things on the other side, I get exactly what we claimed. So this is cool because it means the number of edges in any planar graph is at most linear in the number of vertices. All planar graphs are sparse. It also means that the average degree of a vertex cannot be very big. Just because the summing up all the degrees for this second part, summing over all vertices and then the degree of a vertex, that counts every edge twice, once from each endpoint. And so we know this is at most 6n. And so you can divide by n, and then you get the average. Average degree is at most 6. And because there's it's actually 6n minus 12, you get a strictly less here. That's where the strictly less comes from. Good. Fine. This also means, maybe it's worth listing explicitly, what follows from this, that the average degree is less than 6. This also means I will always have a vertex of degree at most 5 in any planar graph. And the proof is by contradiction. If all vertices had degree at least 6, then the average would be at least 6. It's as simple as that. You call it the probabilistic method if you want. The expected value, if you draw a random vertex, the expected value is less than 6, then there must be a vertex that's below the expectation. Of all this prelude, this is actually the statement that we're going to use. Okay? In every planar graph, there's always a degree of a vertex of degree at most 5. And this property is also called the degeneracy of a graph. So degeneracy is the property that in a graph I can find a vertex of at most that degree, and also if I take any induced subgraph, the same is true. Say degeneracy D. And while we're doing the detour on graph theory, do people know what an induced subgraph is? There's often this notation, if we have a graph GVE, the standard notation I know is this for induced subgraphs. So where V prime is some subset of the vertices. It's a simple thing. It's just the graph where you take the subset of the vertices and you take all the edges of the original graph that only talk about vertices in V prime. A concise way to write this is to take the edges as a set of 2-element sets, or yeah, I guess I'm cheating a tiny bit here. Maybe I should write it out just to be formal. It's all the edges in the graph UV so that U and V are in V prime, and the same edge exists in the original edge set of the graph. That's an induced subgraph. You only focus on a subset of vertices, and you forget of all the edges that would have a dangling end. That's all. But this notation is useful because I think I used it in some pseudocode. So keep that in mind. If you have a graph and then square brackets with a vertex set, that means induced subgraph. And so, yeah, this is. That's that notation. Brilliant. Maybe you also have a feeling now how this independent set algorithm could work. Let me just go back to the claim that we had a while ago. The claim was, if I have a planar graph, I can find independent sets with that running time, 6 to the k times n. Now, this constant 6 popped up here as a bound on the degree or the degeneracy, so maybe this is not so far away. And indeed, the idea is for independent set, if you have any vertex, one of these days again. If you have any vertex and its neighbors, you can only include either the neighbors or one of the neighbors or the center vertex in an independent set. You cannot include both because that vertex in the middle is connected to the others, so they are not part of an independent set. Oops. Okay. This cable. So let me just draw the picture for what I just said. If I have this vertex and its neighbors, if I'm the point is independent sets can be any subset, but if it's an independent set that has any chance to be maximum, so a maximal subset means can't add more vertices to this set. Without making it non-independent. If you have a maximal independent set, you have to take one of those 5 vertices. If you did not include any, then you could have taken the center and added to it. Because you're not including any of the neighbors of this vertex V. None of V's neighbors in the set. could add V itself. So any maximal independent set, any of those that have any chance of being the largest, they must pick either the center vertex or some of the neighbors. They could include many of the neighbors, but at least one of them. That's the idea behind this algorithm. And so what it does is obviously a depth-bounded search. That's still the chapter we're in. So we're given a graph and the parameter, which is the size of the independent set we're trying to construct. If k is larger than the number of vertices in the entire graph, then we're certainly out of luck. Whereas if the edge set is empty, then that's easy. We can just return the entire set. Everything's independent. And otherwise, if we're not in the boring corner cases or base cases, then we have to choose a vertex as the basis for this star. And here we can pick a vertex of minimal degree to reduce the number of choices. So we have a vertex V and its neighbors. And because the graph is planar, we know that this minimal degree vertex will always have degree at most 5. That's just by the magic of planarity. And then we go for each of these vertices, we try including that vertex in the independent set and recurse. One of them has to succeed. Or, well, I should say, if anything succeeds, then a solution with one of them has to succeed. So formally, this looks like I'm constructing a partial solution. I'm constructing the graph where I've removed the vertices that I'm dealing with now. So I remove this vertex and its neighborhood, because if I pick one vertex, I cannot include any of its neighbors in any independent set. So I take the vertex U and all its neighbors. That's what that's supposed to mean. I remove those from the vertex set, and I remove all the edges that have an element in there. So I could have written here GU is G reduce is the induced subgraph on V without D. And then I try recursively to solve the problem where I only look at this graph and I have one less vertex to include. If that solution is indeed successful, I should add vertex U, the center that I picked. So we try this for all the options, either this vertex V in the center or any of its neighbors. And if any of these solutions succeeds, that's great. Then we return the largest of those. Might as well. And if none of them succeeds, then we know there's no possible solution. We've tried all maximal independent sets, and so the maximum independent set can't have size k. So maybe on this slide it's convenient to analyze the search space. We still have to show this running time. So because of planarity, we know D is at most 5, but I have to include V. So we have at most 6 recursive calls in each call. And we may have to go all the way down. Sometimes we're lucky and we can abort early, but in the worst case, we have to go down until k is at 0. That's the is there a base case for k equals 0? How do we stop if k gets smaller and smaller? And eventually the I guess it has to be that the graph gets too small and then we can't continue. So in the worst case, How do we bound the depth? I guess there's a case missing. If k is 0, we should just return the empty set and stop. I don't see if that's somehow implicitly caught in any of the other cases. This is the worst case, that we don't stop before that happens, so we go down with k all the way. And so we branch out 6-fold in each step, and we go k steps down. That gives us a search space of 6 to the k. Again, this is just the worst case. Most graphs won't have the maximal degree equal to 6 all the time. It's actually it's hardly possible in planar graphs, but as a simple bound, that's the best we can say. And then how costly is each recursive call? That depends on how you implement things in detail, but you can say it's linear in the graph size. And so because here n and m are linearly related, each takes linear in n and m, and that here is just linear in n. So the total size, the total running time is bounded by the 6 to the k, and then times n as we had it in the claim. Okay. So one remark is that indeed the 6 to the k may not be the absolute best possible, but some exponential dependence on k is likely not avoidable, because the problem is still NP-hard even on planar graphs, when the vertex degree even is at most 3. So even a much more restricted version of independent set is an NP-hard problem. So you can't expect to solve it in polynomial time, but this FPT time is possible. And the same algorithm works for any bounded degeneracy graph. All we needed, or all we used, was there's always a degree d vertex, a small degree vertex, and then we can bound the running time in a similar way.